Good afternoon, everybody. My name is Saskia O'Sullivan, and I'm the Educational Outreach Officer at the Department of Chemistry at the University of Oxford. And I'm absolutely delighted to be chairing this second live session, which is part of a series of challenges that we've put together with institutions across the UK, part funded by the Royal Society of Chemistry and designed to highlight the many exceptional women who are working in chemistry and who are making a difference in the societal problems that we tackle, and also having opportunities to really change what goes on in the lives of you and me and our families and friends. I've introduced myself. I'm going to ask the three women who've joined me today to do so. Hannah, if I can go to you first. Tell us a little bit about you and what you do at the University of Oxford.
Yeah, so hi everyone, I'm Hannah, and I am a third year PhD student at the University of Oxford. So that means I'm basically studying to become a doctor of chemistry. I already have a chemistry degree. It's just like a bit of extra fun.
Bit of extra fun and working on something that you're really interested in, and you have a great deal of freedom to explore. And perhaps we can talk about that research a little bit later in the session. Holly.
Yeah, hi, I'm Holly. So I'm similar to Hannah. I'm a second year PhD student. So that means I already have my undergraduate degree and I spend my time working on a research project. Yeah.
Sorry, that's my audio going wrong. Holly, that's fantastic. And again, your research has fed into our challenge for this month, which is all about energy. So Megan, how about you?
Hi everyone, I'm Megan. I am a third year undergraduate at Oxford. So I'm still studying my degree. I've got 1 year left. So yeah, that's me.
And of course, as a third year undergraduate, you're about to embark on a research project for your fourth year. And I know that when we last met, you were sort of still exploring what area you might be going into. Have you got an update for us at all?
I haven't put my choices in yet, so I can't confirm. But you know, it's still those areas of exciting energy sources, new ways of powering the world, I guess.
And that's absolutely behind our challenge for this month, which is how do we address the energy demands that the world has without having to rely on fossil fuels, because we know that causes issues with climate change and so on. But also, how do we make that energy portable? Because so much of our modern life is portable. Big thing to do with transport, of course, and of course, portable devices like mobile phones, laptops, the things that you might be watching us on as we speak here today. We've told you about us, but we want to hear from you, and the way in which you can do that. If you're watching us on the website, you'll see next to that embedded live stream is a Q&A channel using Slido, but we hope also that you can see on the banner how to get in touch with us to put your questions in, and just pop those questions into the channel. Any comments you have, we want to hear from you. You could be asking us questions around the challenge that we've set you this month. What has been successful? What have you found difficult? Or indeed more about the research behind the challenge, or life as a researcher, life as an undergraduate, life as a member of staff at the University of Oxford. Any question we'd love to hear from you. Any comments as well. And while we wait for those to come in, then perhaps we can go to the challenge, because we had so many questions in the last session that we didn't even talk about the challenge. So this is a challenge around batteries, because that's what energy is such a big topic. I mean, we've talked a little bit about fossil fuels, we've talked a little bit about portable, but at the heart of portable energy is batteries. Certainly that's how we run our I certainly run my mobile phone and my laptop and so on. I don't have an electric car, but it's an area that is going to become increasingly important with the government targets of moving away from petrol and diesel. So let's think about the challenge, though. The challenge is the first part is to create your own battery. I mean, I buy batteries in the shop. You know, Megan, how did you come up? Because you put that challenge together. How did you come up with this idea of making your own battery, and how easy was it?
Maybe the second question is easier to start with. Not easy at all. I won't lie. It's it's very difficult to make batteries, which is why you do tend to just buy them from the shop. And as some of you probably have figured out by now, there's quite a lot that can go wrong. And it's a bit fiddly, but you know, if you do get it to work eventually, it's really good fun. So I guess that's also why that kind of answers the first question, why? Because it's something we kind of take for granted a bit. You just go to the shop, you buy a pack of batteries, you stick it in the remote, it now works. But actually, how batteries were initially discovered, it's very simple. Stacks of metal that creates the battery, and nowadays we take that for granted. So actually, you know, what goes into it? Hopefully, it will be quite rewarding for you guys to find out.
100%, because I think that peeling back what's underneath a battery. Okay, there are different types of batteries, and perhaps we can get to Holly to talk a little bit more about that. But that basic model of trying to get two different metals stacked up, you know, that was where it started, didn't it? All those many years ago. So it is hard to do, but would you encourage people to persevere with it?
I think perseverance is key. Patience. You are fighting the battery. The battery is trying to win. But you need a lot of patience. It is very tricky. You need to be very precise with what you're doing. But definitely, if you can get it to work, it's really, really worth it.
Definitely a challenge, and that's, I guess, what we wanted to make sure we set out this month. And as you say, very rewarding when you get it to run. So we've got this idea of seeing how battery works, but Holly, your work is very innovative, isn't it? In terms of, normally we're talking about metal ions moving through as an electrolyte, as Hannah will tell us a little bit more about. So a liquid or solid that conducts. But yours is very interesting. Do you want to tell us a little bit more about what you're doing and why it's so innovative?
Yeah, sure. So most batteries have a liquid electrolyte in them. So this electrolyte is there to enable the charge to kind of flow in the battery, and that helps to power, the battery. My work is looking at using a polymer electrolyte. So polymer.
Just stop you. Can you just explain what an electrolyte is? Because you know, if you come across it, then yeah.
So in a battery, you'll have two materials which can store kind of lithium ions, and then in between those two materials you have an electrolyte, which is kind of a substance that the lithium ions can travel through. So that's what an electrolyte is. And my work is looking at making polymer electrolytes. So polymers are these kind of big long chain molecules, and we want to try and use solid polymer electrolytes because they're not flammable, and they can be used in batteries that can store more energy. So that's why we're interested in them. But it is a bit more tricky to kind of develop new polymers, and that's what my project is about.
Because I mean, you talked a little bit about solid electrolytes. I was reading about liquid electrolytes. The reason why you can't put batteries into the hold of a plane is because potentially they catch fire. So does your work, will that solve that problem if we use solid electrolytes?
I think that is definitely the aim of developing better batteries which use solid electrolytes, for sure. Because if you want to put batteries into vehicles, then it is really important that they're safe. Because maybe one day in the future they'll want to put batteries in planes rather than having them fuel powered. We're looking very far in the future, so obviously that would need to be super safe. So that's what we're kind of striving towards, and that's what the research is kind of pushing towards.
And we've got a great question here that's come in from Hannah. Why did you choose batteries as your topic of area of research? Why have you gone for that?
I guess I've always been interested in research that's kind of in the field of energy. I guess I found research which looks at making more kind of sustainable development towards energy sources. That's always kind of interested me. And I also like polymer chemistry, so this has been a really good kind of marriage of the two. And
I was reading as well about sort of new electric cars and it certainly does seem to be that polymers are the way forward to make sort of more powerful and safer batteries for cars. But what's special about polymers? Why are they so good for this? Or I know that's difficult, but yeah. why are they potentially so good?
So some researchers try to use different kinds of solids. So they use solid materials which aren't polymers, and they're kind of really hard. This means that they're really good electrolytes, but because they're so hard, it's difficult to kind of process them in the battery, and they have like quite poor contact with the other battery components. The good thing about polymers is that because they're kind of softer and they're easier to process, they can get really good kind of integration into the rest of the battery. So yeah, that's one of the benefits of using polymers.
So we're sort of, because you typically think of polymers as insulators, don't you? Whereas with a battery, you want the current to flow, you want electricity to power your stuff. So how does that work, where you've got kind of what we would think of as insulators working with something that is charged and flows?
Yeah, polymers are a kind of a really broad class of materials. So what you may know of, what you may think a polymer is, stuff like carrier bags and all that kind of stuff, they're often just made out of carbon and hydrogen. But polymers are kind of any molecule which is kind of a really long chain. So that could be made up of all sorts of atoms in there. So what we're looking at are polymers which have mostly kind of polymers with lots of oxygen atoms in them, because the oxygen could allow the lithium to be kind of transported.
That's really helpful. So the lithium is still the thing that flows, but you're using aspects of that chain to help that lithium to flow. And is that based on charge? Or interactions, or how does it flow?
So the oxygen and the lithium, so the oxygen in the polymer can kind of interact with the lithium because they both have kind of charge or kind of partial charge on them. And the lithium can kind of hop between different oxygen atoms in the polymer chain, which allows it to be transported. And you can design loads of different types of polymers. So I guess that's what my research is about, kind of looking at different polymer designs that can be used to do this.
That's really great. So it's a kind of solid, but that has flow in the hopping. And I know that goes back to our part 3 of our challenge, Megan. So to do with sort of trying to model the flow through the polymers. We know that that's quite difficult to do in lockdown unless you've got a big family or a big family group that you can do. But do you want to say a little bit more about that modelling? I mean, how did you come up with the idea of the tongs versus the tweezers and so on? What were you hoping to do there?
Well, I mean, first of all, I suppose if you don't have a family group, it can be done as a thought exercise. It's not quite as fun, but you can still try and have a think and imagine what would happen. But the way that it's set up is, so in order for the oxygen and the lithium to interact, depending on their sizes, depending on their charges, depending on a whole other factors, they're going to interact better or worse. And so this is kind of designed to help you understand some of the factors that might affect their interactions. So if you have tiny little tongs and you're trying to pick up a ping pong ball, it's quite hard, it might be quite hard for you to grab onto it. And so that would be a poor interaction between the lithium and the oxygen. But if you can match up their sizes and you have some tongs that are the right size to grab onto your ping pong ball, you then have a very good interaction. And so everything flows along much more smoothly. So you can have a play around if you want and see how that goes.
And we are keen, aren't we, to see how people have got on. So there's a way of sharing that with us. We'd love to have your photographs or perhaps miniature film. We've already got one of the films from one of our participants up on the website already. And we're really keen to have more either short video clips or photographs of you actually taking on the challenge. And also we'd like to hear, what do you think is good about that model and what do you think is not so good about a model using tongs and ping pong balls? I've got some more questions coming in, which is great to see. So we've got a question. I think we've answered the question about why choose batteries. Let's stay with the challenge then. So Megan, why do you need vinegar and salt? So and this person, well done to you for having a go at this battery, because as we've already said today, it is really difficult to do. But mine only worked on a multimeter and not on the lap. So I think that's 2 questions really. So I don't know, Megan, do you want to take the question on vinegar and salt, or Hannah, do you want to take that question, given that electrolytes is your specialist area? Why do we need vinegar and salt?
I guess, if Megan, do you want to start by introducing it, and then I can go into more of the theory of it?
Yeah, okay. So basically, plain water in and of itself pure water doesn't really conduct electricity. The water coming out of your taps is probably not pure. It has other stuff in it that can conduct electricity, but water on its own can't. And so that's why I need the salt to add to it, and the vinegar, because both of them will contain ions. The salt, if you know, it contains sodium ions and chloride ions, and they dissolve in the water, and those charged things carry the charge through the water. Same with the vinegar. You get little protons from the vinegar because it's an acid, and so those themselves can carry the charge. So kind of the more you can get in to your water, the more likely it is to be able to conduct the electricity. I guess that's the basics of it. I don't know if Hannah, you have anything else to add?
I think that was yeah, pretty well said.
Yeah, it's really clear.
Yeah.
So what we're talking about then, when we need a battery to operate, is we need something that flows that's charged. And Holly's already talked, hasn't she, about lithium ions. So Hannah, do you want to just sort of explain what we mean by an ion in basic terms, and then how that relates to electrolytes, which is what you're looking at?
Yeah, so ions are just, so like Holly was mentioning about the movement of lithium ions. So you get lithium atoms, and they're just little atoms, neutral, just chilling by themselves. But if you remove an electron from your lithium atom, you get an ion. And because I've removed a negative charge, my lithium is now positive. And this is our positive ion, or our cation. And then what we do to get an electrolyte from ions is we basically take some ions. So, for example, in the challenge, you're using salt, which is sodium chloride. If you dissolve that in water, the sodium chloride will basically dissolve and form ions. It'll form positive ions of sodium, negative ions of chloride, and there you have your electrolyte. You have a material of which can conduct electricity because it has mobile ions within it.
Thanks so much. So we've got moving charge, and that means we've got electricity effectively, or current, and that will power something. We've got some questions coming in on that. So different types of batteries, because you talked a little bit about, so you're making a battery out of vinegar and salt in water. It has to be in solution because, as Hannah says, it has to flow. But if you pick up a battery, if you buy one off the shelf, as you said, Megan, it's easier just to buy it off the shelf. That's not surely got table salt and vinegar in it? I mean, what are in the batteries that you can buy off the shelf? Does anybody know? Anyone going to take that? Otherwise, I'm going to tell you what I know, which is
I guess it depends on the battery and obviously what use it's being used for. Because a lot of, I guess, more modern ones, you'll find solid state batteries, whereby you're not going to be finding like a liquid basically in the battery. But and then there might be batteries which are like higher cost and price, and they may have a liquid like electrolyte, but it won't be the same consistency as like water. It won't be like because you would imagine if you had water in a battery, it would like leak out. So there's like more viscous liquids, which can be used instead. But yeah, you're not going to find table salt.
So they don't. I mean, you're absolutely right. And if you do buy batteries off the shelf, then you can look at the little details that on it as to what is actually found within it. And I think for our challenge, we recommend you use zinc chloride batteries, whereas I don't think the standard sort of AAA batteries that are that. Holly, there's the question that's come in here, and Hannah talked about it a little bit more. Perhaps we can explore this. This idea of solid state batteries and yet electrolytes needing to move. So there's a question here: is the reason solid ionic compounds can't be used in electrolyte as the ions aren't free to move and so can't conduct electricity? Yes. So if you try to use your salt as a solid, you won't get the battery to work. You have to dissolve it in water or in vinegar. But Hannah talked about solid state batteries. Holly, you're talking about solid state batteries. Can you unravel that for us? Can you explain that a bit? And you're on mute.
Got it. Thanks. I can in the context of kind of polymer electrolytes. So something that you have to consider when developing new polymers is the temperature at which the polymer chains can kind of move really easily. So when I kind of make polymers, I want to make a material where the chain can move at a low temperature. So even though the kind of resulting material is solid, the individual chains are able to move. And because of that, the lithium ion can kind of hop between the oxygen atoms and be transported. So yeah, there is movement in solid things, but it's just often more slow.
That's brilliantly explained, because we need that movement, don't we? We need that current. And that's, I guess, the beauty of those polymers, because they're really long. They effectively are solids, even though the chains are moving or helping that lithium to move. I hope I'm answering your questions. Do keep them coming in. They're really great. So there's a question here. Why are there different batteries like AAA and AA? Why do we have all these different batteries? Holly, do you want to take that one?
I mean, I guess different devices have kind of different requirements, essentially. So some devices need kind of different amounts of energy kind of inputted into them in order to work. So I guess that's a key reason. Yeah, and you get batteries made out of different materials as well. So yeah, it was such a wide variety of things that need batteries.
So the power requirements of, say, an electric car is, going to be different to your calculator that you've got to do your schoolwork. Those requirements are very different. Can we talk a little bit more about lithium batteries, because that's what your research is. They are ubiquitous. I mean, they're everywhere, aren't they? They're the key. They're the bit of the Nobel Prize. Our Nobel Prize winning chemistry was about lithium ion batteries. What's so exciting about lithium ion batteries as opposed to, other batteries? Why are we so excited about that?
But yeah, lithium ion batteries are the kind of main battery. That's what most batteries are, and that was the first battery that was developed and kind of used in commercial things was lithium ion. So I guess that's because the lithium ion is really small, so it's kind of more easily transported compared to other ions. Because people do work on different kind of batteries with bigger ions, but that isn't you don't see that as much out and about, kind of outside of the research labs.
Because I was hearing about a research lab that was looking at ions, very commonly found, you find iron in rust, ions are in rust. And they were looking at that because my understanding of lithium ions is that it's quite an expensive way of powering things. I mean, is that a fair comment?
Yeah, I mean, a lot of chemists across all kinds of different fields look for ways to put more iron and kind of replace metals with iron, because iron is so kind of common. Yeah, there are problems with lithium being kind of relatively scarce, or it's kind of finite. There's only so much you can mine. So yeah, that is a problem. There is quite a lot of research going into new ways to recycle the batteries more efficiently. So that is one way you can resolve that.
And I suppose is that a consideration when you're thinking about your polymer battery? You know, one of the things you said was the challenge to make the polymer, but I guess part of it is also what you do at the end of that battery, the life of that battery. So do you have to take that into account as well?
Yeah, so definitely kind of further down the line, there's lots of different factors to consider when you get to the actual kind of battery stage. There's lots of different things you can measure, and there's lots of different things that you need to have a good battery. So one thing is the ionic conductivity, so that's how much charge can it transport. But there's lots of other factors as well. So it needs to kind of last for a long time. Like sometimes the polymer can kind of degrade, or it starts to break down if it's not kind of stable enough. And yeah.
So all of these questions, and I guess you don't, you work in a team, don't you, to answer those? And then there are other chemist roles like process chemists who have to think about how we take the research through to industry and actually make large scale these batteries on a large scale. There's a question here which is around how do you make batteries rechargeable? I mean, is that one of your goals in your research with your polymers, or can all batteries be rechargeable? I mean, how do you make a battery that's rechargeable?
Yeah, I don't actually know why. I mean, certainly the batteries that I'm looking at you would want them to be rechargeable, and the batteries that I kind of read about to help my research and the batteries that I'm trying to make, I do want to be rechargeable, because if they're to be used maybe in cars, obviously that needs to be rechargeable. You can't be throwing out your battery every time you need to refuel. Yeah.
So the question is, how do you make them rechargeable? Do we know that answer, or is that a question we're going to throw out to the people watching and say, tell us in the comments, find out and let us know?
I think I have a rough idea about
go Hannah,
rechargeable batteries. So like everyone's been saying, with the movement of these lithium ions trying to give us our power to power whatever we're using. So let's take we have our normal standard battery, and what happens is there are two electrodes in the battery, and the ions will move from one to the other. And now in a normal battery, once all those ions have moved from one to the other, that's it. Dead, throw away the battery, get a new one. But with a rechargeable one, they go over to the electrode, and then this process of putting in one of those little things that you plug into the wall, it reverses the movement of the ions, so they go back basically over, and that's sort of the recharge discharge cycle. You're on mute, Saskia.
Yeah, I've just realised. I think that kind of answers our question about why does a battery run out of charge. So what you're saying is once all the ions have moved, that's it then. That's a dead battery. And so you have to move those ions back to recharge them. And that's what those little sort of plug in the wall items do. I don't know if we've answered this question. I kind of feel that maybe we could look at it a little bit more, which is around the materials that make the best batteries. And I guess part of that is around kind of what do you want that battery to do. Maybe let's flip it on its head. What are the problems with current batteries that we want to try and solve? Maybe that's one of the things. And therefore, having thought about that, then we can think about what the best materials are. What are some of the problems? Who wants to take that? Holly, do you want to take that?
Yeah, sure. So some of the problems with the electrolyte, which we've spoken about. So when batteries are first developed, they're often used in quite small devices like mobile phones. But now we want to use batteries in kind of bigger things like cars and other vehicles. There's a lot more electrolyte in a battery for a car, and that poses some issues because it can be flammable. And there are kind of very rare cases, but it does sometimes happen where kind of a phone might kind of catch fire. And the stakes are a lot higher if you're in a car, compared to a phone. So we want to try and find a material which works really well in a battery that's also not flammable. And to be able to be used in a battery which stores a lot of energy, which is important for cars because, you don't want to be refueling or recharging, every, 50 miles. It needs to be able to go quite a bit further for people to want to use electric cars. So it's really important that the electrolyte or the polymer is kind of stable so that it can kind of deal with that kind of high amount of energy.
Perfect. Two questions, two problems that we're looking to try and solve. And Hannah, one of the areas that you look at is, we talked a little bit about, batteries don't have salt water in them. And if it was water, then you kind of figured it might leak. And I don't know if anybody's out there who's had this problem where you've got an old battery and it has actually leaked in your drawer if you've left a battery for too long, but it certainly isn't leaking like a sort of a cup of water. But Hannah, you particularly look at this idea of concentrated electrolytes, as you might find both in the battery and also around the electrodes. What are some of the problems associated with that you're trying to solve?
So my I guess approach of it is from more of a very small scale, molecular scale approach. So yeah, you won't really find water in your batteries. This is mainly because water isn't, when a current is applied to it, it breaks down over a pretty short voltage window, which isn't great for batteries. But what I'm doing, although I am using water, I'm basically putting loads and loads of salt in water to make it really, really concentrated. So if you have concentrated squash, that sort of vibe. And I'm basically looking at how these really concentrated electrolytes interact at the surface of the electrode, because it doesn't follow what we're taught as undergraduate chemists about electrolytes and how they behave. We're told, nope, that's too complicated. So I'm studying them, and this was in the hope that obviously if we can develop our understanding of them from the molecular scale, that when it comes to things like developing electrolytes or different processes up to building your battery, that in theory, the theory will help develop better batteries, more efficient batteries that last longer, basically.
I'm muted. It's 2021. I should be used to this. If people want to know a little bit more about that, obviously we've got the whole of the research section on the challenge to find out more, because one of the things that we've certainly talked about in the past has been exactly that. The electrode becomes sort of damaged throughout the life of that battery, and you get these sort of pittings, and so then you're interested in the interactions there. And this is about longevity of the battery, about making it last longer, and so that we don't have to throw them away, because eventually, I suppose, even rechargeable batteries have a finite lifetime. Got still questions coming in, so thank you everyone. Keep them coming in. There's a question here. So it's a question about loads. Is there anything that is an alternative for a battery? Let's take it right back then. What does a battery do? Holly?
Yeah, so batteries are there to kind of provide energy for a device. So I guess there are other ways you can provide energy as well. So anything that can cause a rotation is able to provide energy. So this is a silly example maybe, but sometimes I've seen people hook up TVs to an exercise bike, and if you cycle, you can power the TV. But that's kind of how fossil fuels work as well. So if you burn fossil fuels, the heat is used to kind of turn something, which then generates energy. Yeah, I'm not sure what other examples would be.
So those are all things that are running as you are generating your electricity, aren't you? By friction on the bike and by turning a turbine to do that. But I think you hit the nail on the head, didn't you? That it's a way of providing energy on demand. That it sort of stores the ability to do that, doesn't it? But it's not stored as electricity.
Okay, yeah. So I guess other ways, a really basic way that energy is stored, for example, is in like wood. So if you burn wood, that produces energy. Something which is more very much kind of in research labs is that you can, some chemicals like ammonia in research labs is being looked into for energy storage, because if you kind of break it down, it releases nitrogen and hydrogen. And when it releases these gases, that can release energy as well. And that's very much kind of more fundamental. It's not, widely used at all. But yeah, there are other ways to store energy, but not as commonly as batteries.
And it's back to that thing about where our sort of modern life is designed around these batteries, isn't it? So it's how to make them better for the environment, more efficient, less flammable, safer. All of those questions that are important. Meanwhile, other people are looking at completely novel ways of storing energy, like you said, with the ammonia. We've still got questions coming in, so we'll keep to those. So which acids can be used? I'm guessing this is back to the challenge. So we talked about vinegar being an acid. There's a question here, can you use sulfuric acid? Megan, did you try sulfuric acid?
I didn't try sulfuric acid, but the reason why we said vinegar is because it's a relatively weak acid, so it's just much safer to use. It doesn't matter if you get a bit on your hands, but in theory, any acid should work, because when you dissolve it in water, it will release protons, which are positively charged hydrogen ions, and those will help carry the charge as well. So I didn't test it because sulfuric acid is a bit stronger, but any acid would work.
And I'm guessing part of that is also reactions that might happen with other materials that you've got as part of your battery. So you don't want any side reactions, do you? You really want it to flow as opposed to sort of do anything else. Okay, so where are batteries made? Good question. Hannah's looking bemused. We don't know. I mean, we know that batteries are made in research labs because that's what we're doing. But in general terms, in sort of commercial batteries, I mean, I was reading about Nissan, who's obviously that in the news around electric cars, but they're looking to invest in the UK for making polymer-based batteries for their cars. But I'm guessing there's manufacturing of batteries across the world because of demand. But yeah, we don't know the answer to that, do we? Like definitive answer. So I'm afraid we don't know the answer to that one. Let's go on to when a battery eventually breaks down, degrades, can it be reused or recycled well?
It should be able to be recycled. I think the kind of amount of used batteries which do get recycled is very low. But it should be possible to recycle batteries, but it can be quite difficult because there's so many kind of components in there which are all kind of combined. So it is tricky, and that is an area of research which people are working on, to kind of find better ways to recycle batteries so you can recover more of the material.
Brilliant, thank you. And I've got a question here. Is a battery leak harmful, and if so, what makes it harmful? Holly, do you want to take that? Because I know that's one of the things that you're looking to try and address.
Yeah, sure. So yeah, batteries are all kind of contained in a casing, which is partly so they kind of work better because you don't want things exposed. But it is also important to keep everything in because it isn't good for the environment. So some of the things in a battery might be toxic. It could be, if you get it on your skin, it could could have burn. It's the things in a battery are hazardous. So yeah, it's important to try and keep everything inside the battery. That is one of the benefits of using a solid electrolyte. It is less likely to kind of escape from its casing.
Thanks. Okay, so do batteries break down easily? If you've asked that question, maybe come back to us and explain a little bit more. Do you mean in terms of the end of life of that battery? I'm not quite sure what that question is, so come back to us because we want to answer your questions, and we've got 20 minutes to do that in. So how easy is it to supply direct current? I'm guessing from a battery. Anyone know? These are great questions, but I don't know if we know the answers to all of them. Hannah's looking extremely unsure.
I mean, if you're looking at it from, maybe this is more physics, but I think batteries do tend to supply direct current, because you have the battery, what releases the energy is, if you want to think of it this way, it's essentially a chemical reaction that releases the energy. And if that's happening all the time, you're going to get energy being released all the time. So you get direct current generally for batteries because it's happening all the time. But you might get alternating current, which is what comes out of the sockets in your house. It's what the power grid is, it's alternating current. You might get that if you make your electricity from another method, which is you might have seen in physics. You can make electricity with a little magnet, and you spin some copper wires within the magnet, and because that's, it's flipping over, you get current on, current off, current, and so you get the alternating current. But batteries are pretty much always going to supply direct current.
Brilliant, thanks Megan, that's really clear. We've got a question about cryolite. I think that's added to an electrolyte to reduce the melting point. So I think we're talking here about extraction of metals, aren't we? And there's some question then, I guess, about additives. I mean, in your line of work, Hannah, do you, because I know you look at different salts, different electrolytes, do you look at electrolytes in their purest form, or do you ever look at mixtures, and is there any difference?
I haven't looked at mixtures, just because on the sort of molecular fundamental theory side, the more that you put into something, the more complicated your model becomes. So yeah, I haven't. I wonder whether or not Holly knows any more about like additives.
I mean, one of your areas is that you are looking at mixtures. Do you want to tell us a bit about that?
Yeah, so I'm not too sure about cryolite, but in kind of battery research in the labs, when people use polymer electrolytes, sometimes they do put in an additive, and often the purpose of this additive is to make the polymer more flexible. So if it's more flexible, it's able to kind of transport the lithium ions more easily. So maybe it isn't. Some people might try to make polymers which can just work by themselves, because that is, it's a cleaner solution. But yeah, people do use additives to improve the performance of the electrolytes.
And one of the things that I know your research is also to do with the electrode, isn't it? And using polymers in there. Do you want to tell us a little bit about that work? Yeah,
sure. So the purpose of electrodes in the battery is to store lithium ions. And when a battery is charged and discharged, they move from one electrode to another electrode. When lithium kind of moves into an electrode, it causes like the electrode structure to kind of expand. And this can damage the material when you start to get like cracks and you lose contact between the components. And this can make the battery kind of start to break down, essentially, which I guess goes back to that question you asked earlier, maybe. So one way that polymers can be used here is to have the electrodes kind of mixed up into a polymer, because this polymer can be quite soft and it can kind of contract and expand with the electrode to kind of reduce any damage.
Sounds brilliant. Okay, I've got some more questions for you then that have come in. Are there any other things needed, like high temperatures, Oh, okay. So this seems to be around ionic compounds being molten in batteries for direct current. I'm guessing we're not looking at molten at all, because we need things to work at sort of room temperatures. Any comments on that? Just
yeah, so molten, just like molten salts, for example, you won't find in batteries because the melting temperature is so high. But there are a really interesting class of liquids known as ionic liquids, which are effectively molten salts, but they are a liquid at room temperature. The problem is they're expensive, and you probably wouldn't find them in day-to-day use of batteries.
brilliant, thank you. So we got some questions again, more about common electrolytes. So and this kind of relates to the question we were talking about earlier about lithium, the use of lithium. Because it's small, it's a very good electrolyte to use. The question here about aluminium and abundance. I mean, Holly, you talked a little bit about work on iron. I mean, iron ions. So stuff you get in rust. Is aluminium a contender for an electrolyte? Do we know?
Yeah, I'm not totally sure actually. I don't think I've heard anything about aluminium. I don't know much about aluminium. No.
So we don't know that question. So we don't know that answer. So this is something that perhaps those who are watching, who are curious, could let us know in the comments, or send us in a short video about what you found out. Okay, so redox reactions. Do redox reactions happen in batteries, Hannah? And what is a redox reaction for those of us who don't know?
Yeah, this is going back a while. I haven't thought even of the word redox in so long. So a redox reaction is basically the couple of a reduction and an oxidation. And these are basically the addition or loss of an electron or electrons. With the other one, basically you have these two systems working in parallel, and if you were to lose electrons from one, they will go over, and that one will gain electrons. Redox chemistry in batteries, I feel like Holly might be better to answering this with regards to lithium ions going within your layers. I can't remember whether or not it's redox or not.
I'm not I think they exist as ions the whole time, but I'm not totally sure, to be honest. In research, again, this isn't maybe used so much, more widely. You can get some batteries which have one of the electrodes is made out of lithium metal. So in that case, in the electrolyte, you'd have lithium ions, and then when it would get to the lithium electrode, it would then be a lithium atom.
But I'm guessing if a battery runs out, then clearly the sort of cation is not able to flow and move and pick up an electron, and then my understanding would be that potentially it is redox. I mean, I'm just spouting off here in terms of that movement of electrons in the current, but yeah, I mean, I might be completely wrong.
I think it must be, because the lithium atom at an electrode, the lithium atom splits into an electron which goes around the external circuit, and that powers your device or your phone or whatever. And then the lithium ion will travel through the electrolyte. So at the electrode, the lithium atom splits into an electron and a lithium ion, and I suppose that counts as a redox.
Yeah, in terms of losing its electron, absolutely. So being oxidized and then, I guess, reduced at the other end once it's traveled through and the electron has traveled around the circuit. Okay, so we're going to keep going. And What are the most efficient batteries, and what makes them efficient? Gosh, great question. What makes efficient batteries? Who wants? You're challenging us today, I have to say. So, anyone wants to take that question?
I mean, I guess if you're saying if you're wanting an efficient battery, that means something where as much as the energy as possible is like transferred to electric energy. So this doesn't necessarily mean the best battery, but the most efficient would waste as little energy and kind of heat as possible. So I'm not sure what that would be, but that is what an efficient battery is. Yeah.
I can bring this back to the challenge.
Yeah, go for it.
If people are, just because this is one of the big problems with doing the challenge. If you guys have come across this problem, it's making batteries with stuff in your kitchen is not very efficient because it tends to lose a lot of energy. If you're using tinfoil wires, even copper wires, when electrons travel through the metal, they're going to hit everything else in the metal because it's all made up of atoms. So the electrons lose energy that way, and a lot of it gets transferred into heat. So a lot of the battery troubleshooting is about making it more efficient. So this is why you have to clean your coins if you're using coins. This is why you need to make sure you always have good contact. So, it's pressed together as tightly as you can. You clean everything. Wires are wrapped around tightly, because if you start making electrons hop across gaps, or, you have very long wires, so it's got a lot of atoms to get past, it just makes it very inefficient. So that might be something you guys are struggling with, the efficiency of the battery. You're probably making a very good battery, but very little of the energy can get out.
That's really helpful, and we notice that, don't we, in terms of our devices? They get very hot. Your phone gets hot if you're using it a lot, or your laptop or whatever. So part of it is the design of the battery, I guess, and part of it is also the design of all the housing and the electrics that go around whatever you're powering. We've got a question coming in. So what energy stores are transferred to other energy stores when a battery is in use? I'm guessing that's kind of around, what are those energy transfers from a battery through? I mean, are we talking, do we think that we're going to energy stores, or effectively is it being transferred into, kinetic energy if you're moving something, or and so on? Does anyone want to take that?
I suppose they're transferring kind of chemical energy from the electrodes into electrical energy. Yeah, I think that must be what the energy transfer is in a battery.
I'm on mute. I'm on mute. Some couple more questions. I have to say, I'm going to disappear because the University of Oxford has decided that my computer is about to restart and there's no way I can stop it. So I need somebody to take over chair.
Okay, I think we might have lost Saskia.
I also think we've lost Saskia. Okay, so we've got 6 minutes. So if we just pull up the Slido, we can go through a few more of the questions. So if you guys give us like 2 minutes while we just get it up, as Saskia.
Okay, I am back. I think I'm back. I'm actually on my device. I'm on my mobile phone. I don't know if you can see me and hear me. Brilliant. So this is one of those wonderful moments where a software update that you can't kind of avoid and can't cancel has been foisted upon us. But there were a couple of questions that came in just as I was disappearing, courtesy of the IT system. Has anybody picked one of those up from the chat? From the website? Not yet. Okay. Well, let's get those up. We were talking about. I think there was a question around. Actually, I'm just making this up. So, can we just grab through to the Slido? I've literally only got a mobile phone.
I could ask Holly if you want to. I've just got the questions up. So Holly or Hannah, would you want to go on? Are there any compounds or substances you couldn't use for a battery?
That was the
Too
question
reactive.
I Brilliant. Yeah. What can't we use?
Yeah, I'm not sure about kind of naming specific things, but I know, so one of the problems of using batteries with lithium electrodes is that they can be quite reactive, like they can degrade quite easily. Another problem of using lithium electrodes is that you can kind of get growths of lithium strands almost like growing across the electrolyte. So that's a big problem with using lithium electrodes. There's problems of lots of different materials, and I guess that's what people in research labs try to do. They try to kind of overcome problems with materials so that they can make batteries better. So
in some ways, lithium is our best bet for now, isn't it? It works. We've got a yes, it was Nobel Prize winning chemistry, but we're constantly trying to improve batteries because it works, but it isn't perfect. I mean, is there such? Do you think we'll ever get to the point where there's a perfect battery?
No. I mean, you can always make improvements, can't you? And I guess as you make new technologies, the requirements change. So you might be able to make a perfect battery for the year 2021, but then once we get to that point, we'll have new things which we want from a battery, because 30 years ago they weren't trying to make batteries for electric vehicles. So yeah.
So I mean, you mentioned it earlier, didn't you, about flight? The idea that we could potentially, I mean, they've proven, haven't they, that you can take a plane with a very large wingspan with solar panels on the wingspan, that with kind of like two people, can fly around the world, right? And presume, because it's not sunny the whole time, they're having to use batteries there to continue the flight when it's at night. And I'm guessing, whilst that's a proof of principle, one of the applications of the research that you're doing could be for future flight that's electric. I mean, that's completely mad, isn't it? The idea that we can get up into the air just using batteries as opposed to jet fuel.
Yeah, I mean, that would cause kind of more kind of challenges, because I guess they'd be operating at much colder temperatures. They need to be even more safe. I mean, that would be super important. They need to be light. That would be important as well. So yeah, as we kind of are more ambitious of where we want to have our batteries, you have more challenges to overcome with designing them.
And I'm also thinking, this is the year that we've sent another rover to Mars. I mean, space travel, let's dream big. But if you're thinking about batteries that could be used for a rover on Mars, that's going to be even more challenging in terms of the materials there and how long they last and so on. Megan, we've got kind of a couple of minutes. You've got the questions in front of you. Have we missed any? Because I know there were two that were ready for me to ask when I disappeared. Apologies for that. Bit of a shock.
Someone's asked whether lithium ions are flammable and how they're transported.
Holly, to you, I think, again.
I mean, I guess you don't have the lithium ions are always in an electrolyte, so you're not really dealing with them as they are. So if they're in a kind of liquid electrolyte, that can be flammable. But if you use a different kind of electrolyte, then it may not be flammable. So yeah, but yeah, lithium metal is flammable. But, yeah.
Yeah, you may have seen that at school. There's a fantastic, obviously, school demonstration around lithium metal, which reacts very readily with water and produces hydrogen gas, which is of course then flammable. So lithium itself won't auto-ignite, but the hydrogen gas, if there's any flame around it, will ignite. And depending on how large a lithium piece you've got, depends how large your little explosion is. But it's great fun. So if you haven't seen that, do ask your teacher to show you, or there's some great YouTube clips on it as well. We are out of time, and I have to say, it's been fantastic today. We've been really challenged by your questions. They've been excellent. We're really excited to be working with you, and we hope that you're going to send us more questions, more comments. Delighted to read, of course, that people are trying the challenge. Yes, it is challenging, but let us know how you get on. Send us photos of how you're doing, and of course we love to see those videos as well. Best of luck. We'll see you next Friday for our final live session, and we're going to be joined by Professor Charlotte Williams as well, another member of the team behind the challenge. So we're really looking forward to seeing you then, and take care in the meantime. Thanks for joining us. Bye bye.